So
You grew very much.
you can see the recording later. So PI compensator and controller or lag compensator. We studied this last time. So this is the recap or summary of the what we studied last time. So lag compensator is a approximation for the PI compensator. So both are similar. Just there's a little difference in the transfer function. So PI or lag compensator is used to improve the steady state error. And the difference, main difference is that the PI compensator, they are made from the active circuits, whereas the lag compensator, they are made from the passive circuits. And both are used to improve the steady state error, but they does not affect the transient response, or you can say the dynamics of the system. So in PI compensator, we place the pole at exactly at the origin, okay, and then choose the 0 at some left side of the origin, very close to the origin pole. But in the lag compensator, we do not choose the pole at exactly at 0, but we very near to the 0, and then on the left side we choose 0, base 0, which is also near to the pole. But the disadvantage is that lag compensator does not drive the steady state error exactly to 0, but very close to the 0, minimize there. But PI compensator, they drive the steady state error exactly to the 0. The PD compensators, they are on the other hand, they are used to improve the transient response. They have very little effect on the steady state error. So they actually are used to change the dynamics of the system. So in PD compensator, we place the 0 at some appropriate location. So one method of PD compensator is that we place the 0 at a position such that it cancel the 0, cancel the pole. Okay, this is one of the simplest method. So, and the lead compensator, we have it is the same, but it's approximation of the PD compensator. It improves the transient response, and it's built from the passive circuits. Again, it has a 0 and pole. So pole is on the right side of the 0, on the left side of the 0. So first we choose the position of the 0 as close to the origin in a position such that it cancels the pole, and then we choose the pole on the left side of the 0 so that to compensate the some angle efficiency. We will see the examples, numerical examples, and you have the idea. So last time we I think we did this example. Let me see again. So the example says that design a PD compensator to build 16% overshoot to yield 16% overshoot with a 3-fold reduction in the settling time. So this is the requirement. Required, you can say the time domain specifications. The plant is given here. So you look at the plant, you see that it is third order system. So in order to meet these transit specifications or time domain specifications, we have to convert or transform this third order system to the second order system. So this is the first step, because all of the damping ratio, overshoot, settling time, time domain specification, they are applicable to the second order system. So first we approximate this third order to the second order system. So the first step is to we draw the root locus of the system, given system. For k vary from 0 to infinity, this root locus can be drawn in MATLAB very easily. So from that root locus, we will choose some dominant poles. How we choose the dominant poles? So first, let's see, we'll find what is the damping ratio of the system, this given system, right? So in given system, you see that about one requirement is given that overshoot, percentage overshoot is 16%. So using the relationship between the percentage overshoot and the zeta damping ratio. This is the formula of this one, so we can calculate the zeta. So once zeta is given, so we can use this formula for the dominant poles. So there are two poles we can choose. So this is the zeta line. So we draw the zeta line. So the line, the where it cuts the root locus. So that point we choose as a dominant pole. S1 here, S2 will be complex conjugate will be over here. So that will be the formula for the minus zeta omega n plus minus j omega n 1 minus zeta square. So this is the formula for the dominant poles or secondary.
Root locus
Root locus
is here.
Yes.
This is and zeta
line is this one. This one. Let me draw it. So this is zeta line. This is zeta line. Right. So this zeta line is also you know that how we draw this zeta line. We know the
yes for now
angle
theta is
cos of for something zeta is equal to anything theta is equal to cos of
that is arctangents
some I think cos inverse of
tangents
z. From this formula you can draw this line. So this line cuts the root locus at S1. So that is our dominant poles. So once we find the dominant poles of the given system, so first we calculate the angles to this this pole, right? So how we calculate the angle means the given pole 0 are on the real axis. One is -4, 0 -4 -6. 0 -4 -6. So from that we calculate the angle of this. So first theta1, theta2, theta3. So theta1 we can calculate using this triangle. Using this triangle. So this. So this point is 0.5. That is 0.5 mega n. This point is a point. What is that? 0.85. 0.5. So this one 1 minus zeta square under root underscore. If you calculate this one, it will become 0.8 something. And omega n. So the omega n is not known yet. We want to find as omega n. So that's why we are using this angle condition. So this angle is calculated from theta1, then theta2 is calculated from this triangle, and then theta3 is calculated from this triangle. There are 3 right angle triangles. We can calculate theta1, theta2, theta3. You got the idea how to calculate this?
It is.
So this
yes because we have imaginary number and we have the real number. And from imaginary and real number, we using this arctangents because tangents is 1.
So this this length is 4 minus this one.
Yes.
This length is 6 minus this one.
Yes.
So omega n. So from here we can calculate the omega n, right?
Yes.
Use the angle condition. What's the angle condition? That if
plus minus 1.
Yeah, if you know that if a pole is on the root locus, its angle from the open loop poles and zeros should be odd multiple of the plus minus 180 degree. That is the condition for. So if we add all these angles, it should be equal to plus minus 180 degree. So from this equation, our aim is to calculate the omega n. Unknown variable is omega n. So if we do some calculation to use this property of the tangent a plus b is equal to this one, and finally we manipulate these equations to get the omega n this. So once we know omega n, so we exactly know where our dominant poles are lying. The dominant poles are at this according to this one. Zeta we have calculated already. Omega we calculated from here. Then this is our dominant pole of the uncompensated system, given system, right? Not given system, approximate given system. Approximate dominant poles of the system. So
We will make the approximation from the third order
to the second.
to the second order.
And these are the two poles of the dominant poles, which lie on the root locus. So next, now we look at the desired time domain specification and find the required time dominant poles. So first, we see what is the requirement for the time domain specification. The requirement is that settling time is settling time is a given system 4 over zeta omega n. This is the formula. So we know this omega n, we know zeta n, omega n, zeta n will calculate. So this is the settling time of the given system. Settling time of the new system, it says 1/3. According to the problem, it says that the settling time should be this percentage also with a 3-fold reduction, 1/3, right? Meaning at 1/3 of the given system. So settling time should be 1/3 of the given system. So given time this one, so 1/3 is this one. Okay, so if this is the new time settling time of the new system, the desired system actually. So this is equal to, if we use again this formula, 4 over zeta omega n new. So from here we also need to calculate what is the new omega n. Zeta will remain same because there is no condition that it says maintain the same damping ratio. So zeta will not change. Only the omega n will change. Settling time will change, omega n will change. So from this formula, we can calculate the new omega n. So this is equal to 4 over zeta is given. So omega n, new omega n is given this. So if we know the omega n, new omega n, we know the zeta new is same as the old zeta, right? So this is same as the old. There is no change. So we can find the dominant pole, desired dominant poles. Now they are the desired poles. So desired dominant pole will become the zeta omega new plus minus omega new. So we plug in this is our desired poles, desired dominant poles, second order poles, right? So you see that I listed here just for the clarification. So this is the given desired pole, given dominant poles. This is the desired dominant poles. So this pole is on root locus, right? This is already on root locus. But if we draw this is not root.
Yes, because it's
minus 3 plus 6, it will be somewhere else. It's not on the root locus. So the current root locus is not passing through the desired pole location. It means that we have to modify the root locus so that the desired pole lie on the new root locus. If new desired poles have to lie on the root locus, they must satisfy the angle condition. This is, of course, the design condition must satisfy. So let's calculate the current angle of the desired. So where desired pole lies somewhere. So let's calculate first what is the current angle of these poles is from the given open loop poles. Open loop pole is at 0. Open loop one is at -4. One is at -6. So this is our desired this way. So again, -3 real part is here, imaginary part is here.
We can calculate that.
So we can calculate theta also, and theta 1, theta 2, theta 3 we can calculate with easy, right? The right angle triangles. So if you calculate these things, so the angle is of the desired poles is -275. It is not equal to 180 degrees. It means that it is not on the root locus. What is the angle deficiency? Angle deficiency is 95 degrees.
We need to add this.
And we need to compensate this. Compensate this angle. So how we compensate this angle deficiency? By reshaping the root locus and forcing the root locus to pass through the desired poles. Root locus can be reshaped by placing a 0 in the current system. Adding a 0 with the will drag the root locus to the left of the S-plane. The angle deficiency -5 degree can be compensated by adding a 0 at plus 95 degree by putting a 0 at at this position we should add. So This is our desired pole location. So where we should